Hi, I'm Megan, and in my physics class we made mousetrap cars. And I'm just going to talk a little bit about how mousetrap cars relate to physics. First of all, this is my car. It is called the Big Cheese, with wheels that look like wheels of cheese. And here is the mousetrap, which is obviously the base of the vehicle. It takes up the main body area. And these are CDs here for wheels, and the axles are hollow pen cylinders. And this weighs about 124 grams, and it moved very nicely, about a distance of 4 meters in the test run. Now, the first thing I want to talk to you about is the kinematics of this car, which is really just how the car moves. First, watch a video of how it moves.
2, 1.
Are you trying to prove something to yourself?
Oh, that's far.
That was awesome! Now, let's take a look at some graphs of how that car moved to analyze it further.
This is the position versus time graph with time on the x-axis measured in seconds and position or displacement on the y-axis measured in meters. Here, this curved slope shows us that the car was speeding up, and the slope of the line also represents the velocity of the car in motion. And here is the velocity versus time graph with time still on the x-axis in seconds and velocity measured in meters per second on the y-axis. This line here shows us the rate of acceleration, which is about 4.611 meters per second squared, and the total change in velocity is about 5.827 meters per second. Again, we can see not only that the car was increasing in speed, but that it was also, for the most part, increasing in acceleration. And now here we have the acceleration versus time graph, with time still on the x-axis in seconds, and acceleration in meters per second squared on the y-axis. This line looks different because it has an obvious turn in it, and on its way up, at the beginning of the time and the car's acceleration, we can see that the line is in a positive direction, which means that the car was accelerating, increasing in acceleration. And at about 3.25 seconds, we can see that the car makes a shift. Not in its position, but it starts to decelerate.
From observing the motion of the mousetrap car, we can make graphs to analyze how the car moved. And now we know that the car had increasing and positive velocity and increasing acceleration until about 3.25 seconds when the car began to decrease in acceleration. Now, it's important to remember that this did not mean that the car started to slow down. It only decreased in the rate at which it was speeding up. Now that we know all about how the car moved, let's talk about what made the car move. That's forces. Newton's second law says that force and acceleration are related by mass. He's talking about how mass times acceleration equals force. In real life terms, think about an 18-wheeler and a bicycle. They could both be riding along the street at 10 miles per hour and even having the same acceleration, but that 18-wheeler is going to have a whole lot more force than the bicycle does because it has so much more mass than the bicycle. Or think about a bowling ball and a golf ball. You can drop them both from a 100-story building, and they're both going to accelerate at the same rate of 9.81 meters per second as they fall down. But the bowling ball is going to have a whole lot more force because it has more mass than the golf ball does. So we're going to look at this on terms of our mousetrap car now.
Here we have a free body diagram for the car in movement. As you can see, each of the arrows in the free body diagram shows a different direction of the forces that were acting upon the car. The downward arrow, labeled FW, is the force of the weight of the car. pushing down on the ground, and Fn is the neutral force back of the ground pushing back up on the car. We know that these forces were balanced because the car remained on the ground, neither sinking into it or floating above it. This is an example of Newton's third law, how forces come in pairs that are equal in opposite directions. The next step in calculating the forces is finding the rectangular coordinate values of each force. So we know what the force of weight is, which is essentially the mass in kilograms times 10, which ends up being 124 newtons. So our rectangular coordinate would be 0 and then negative 124. Negative because the force of weight arrow points down on the free body diagram, if you remember. And we need to find the neutral force. The force of movement we know because we can multiply the mass of the car in kilograms times the acceleration of the car. This is the equation F equals ma. And then we're looking for the friction force. The rightward arrow is the force of movement, the direction in which the car was moving, and the opposite arrow is the force of friction. Now we will set our equations for the x-axis and the y-axis equal to mass times acceleration, because mass times acceleration equals force. So, for the mass times the acceleration on the y-axis, we have force of neutral minus force of weight. Now the mass and acceleration on the y-axis is 0 because we have no acceleration in the vertical direction because the car was not going upward in any way. And we get the force, the neutral force, to be 124 newtons. And then we do the same for the x-axis, except the car was accelerating in the horizontal direction, so we multiply the mass of the car in kilograms times the acceleration, and then we can solve to find the friction force. The force values come out to be 124 newtons in the force of weight. The neutral force is also 124 newtons. This is proving Newton's third law to be true, that forces come in equal and opposite pairs. And the force of movement is 571.764 newtons, and the force of friction is 574.192 newtons. And this makes sense because the force of motion is greater than the force of friction, not by much, but it shows that the car was able to move forward and the force of friction was not overpowering it.
The forces that made my car move also made my car have momentum. Momentum is mass moving with velocity, and you can get this by multiplying mass of the car times velocity. The momentum of my car was about 0.722548 kilograms meters per second. That's not very big, but it's still some momentum. A better way to think about momentum might be with another 18-wheeler and a bike. The 18-wheeler and the bike could be traveling at the same speed again, let's say 10 meters per second. This is their velocity. But since they have such different masses, the 18-wheeler is so much bigger than the bike, and that mass is going to produce a much greater momentum than the bike would. Or the bike could travel at a much greater speed than the 18-wheeler for some reason, and then maybe it could have a greater momentum than the 18-wheeler. Just something else to think about. The last thing we're going to talk about is the changes in energy that was happening with the Mousetrap car. First of all, there are two types of energy: kinetic, the energy of movement, and potential, which is stored energy. A Mousetrap car is designed to run on potential energy stored up inside the wound up string in the Mousetrap car. And as you can see here, if you can see it, there is an axle with string wound around it. And we have this, it is attached to the arm, and when you pull it back and tighten it all up, potential energy is maximized. This is elastic potential energy, by the way, because it's stored in a spring. The other kind of potential energy is stored by having a height. So I'm pulling the arm back here, and when the arm is released, the string is let go, and this potential energy is converted into kinetic energy, and that's how the Mousetrap car moves.
This is an image explaining the changes in kinetic and potential energy in the Mousetrap car. We know that the Mousetrap car started off with a full amount of potential energy stored up in its spring. When the spring was released, this potential energy changed into kinetic energy as the car moved. Before the car stopped moving, at that very instant, the car was at its maximum kinetic energy. The car started off with full potential energy and ended up with full kinetic energy. This is known as the conservation of energy, where the potential energy in the beginning equals the kinetic energy that it finishes with. In other words, the total amount of energy in the system remained constant over time. That's why it's called the conservation of energy. Next, we can use this equation here to calculate the values of our energy. We know that kinetic energy equals mass times the velocity squared divided by 2. We know the mass of the car, which was 0.124 kilograms, and the velocity, which was 5.827 meters per second. After filling out this equation, we find that the kinetic energy equaled 2.11 joules. And since we know that potential energy equals the kinetic energy, potential energy must also equal 2.11 joules.
The conservation of energy law better. There's a spring against a wall, a fixed spring, and it's kind of sticking out. And you can press a box against it and push that spring all the way back towards the wall. And when you let go of that box, the spring will jolt back at you. Now, when the spring is all the way flat against the wall when you're pressing on the box, that's all of the elastic potential energy. It's full of elastic potential energy. And when you let go and that spring releases and the box is in motion, that's all kinetic energy. And if you want an example with gravitational potential energy, think about a box on the top of a 100-story building. That's a lot of height. That has a lot of energy stored up from gravity. That's gravitational potential energy. If you kick that box off the top of the building, right before it hits the ground, it's going to have full kinetic energy. That's all of its motion energy. It doesn't have any height anymore because it's basically on the ground, but it's in full motion. So there's a lot of kinetic energy there. We've now covered a ton of great information about how velocity and acceleration and kinematics graphs all pertain to the motion of my Mousetrap car, and then we talked about how force and momentum affects the motion, and then we talked about how energy transformations have an effect on the car. It's great. We covered so much information in this video, and I'm so happy you could watch it. And I highly encourage you to go make one of these Mousetrap cars at home because you will learn so much about physics.